Okay, welcome to our first section in Math 230. So I'm going to be rather quick here to make the video short. So we're looking at two-dimensional systems versus our three-dimensional system. So if you wanted to plot a point, say AB, we'll go to the right A, up B, plot our point AB. In a three-dimensional system, you have your positive x, positive y, positive z. So it's your two-dimensional xy coordinate plane with a vertical line going right through the origin. You can go negative x's, negative y's, negative z's, label those if you want to make sure you're in the right spot. So if you want to plot point ABC, A goes along the x-axis, B goes along the y-axis, C goes along the z. So what I would encourage you to do is to plot this point. Take your pencil, mark it off, go parallel to the same distance, stop, mark this distance with your pencil, whether you're pinching it off, whatever you got to do. Use a ruler if you want, or the edge of a piece of paper. From this point, go straight up, and there's going to be your point ABC. This is 2 dimensions here, 3 dimensions. Ordered pair in R squared. This means real number squared, so that means our 2-dimension. You see R to the third power, that means an ordered triple in our 3-dimensional space. Equations in 2-dimensional, and xy usually represents a curve. Here, xyz is going to represent a surface. For example, a plane. And we're going to use the right-hand rule to build our xyz coordinate plane. So think of your wrist of your right hand as your positive y-axis. Your thumb pointing in the air is your positive z. Then your fingers pointing at a 90-degree angle away from your wrist would be your positive x-axis. We have 8 octants. So in a 2-dimensional, you have quadrant 1, 2, 3, 4. 3-dimensional, think of your xy plane. There's quadrant 1, but now it's 3-dimensional, so it's octant 1. You still rotate around counterclockwise. Octant 2, 3, and 4. To get to octant 5, now below octant 1, on the negative side, below the xy coordinate plane, octant 5, and then we go around counterclockwise again. 6, 7, and 8. Some of the formulas from your 2-dimensional space to 3-dimensional space are pretty much the same. If you had to find the distance between 2 points in 3 dimension, it's the same distance formula. You just add the extra second z coordinate minus the first z coordinate and square it. The equation of a sphere, just like the equation of a circle, x minus h squared plus y minus k squared, we just add the extra binomial squared for the z coordinate. That's your r squared. If we're at the origin, no h, k, and l being added or subtracted. If I cover up the z squared, there's your traditional circle. Putting in a plus z squared makes it a sphere. Midpoint formula, you might recall this. This is where you added the x's and divided by 2, added the y's and divided by 2. Just do it for the z's as well. Add the z's divided by 2 gives you the midpoint between any 2 points in a 3-dimensional space. If we want to show the representation and explanation of y equals 5 in our 2-dimensional space and 3-dimensional space, y equals 5 would just be considered your horizontal line. It's a set of all points xy such that y is 5, x can be any value. Take that into 3-dimensional, go to 5 on the positive y. Now that line has to have height, depth if you will. So now you're going to have a plane parallel to the xz axis, and it's going to go up and down in the direction of the z-axis and left and right in the direction of the x-axis forever. So ways you can explain it, you can say a set of all points x, y, z such that y equals 5. X and z can be any value. You could also say you have a vertical plane parallel to the xz plane and it's 5 units to the right or positive direction on the y-axis. Let's say we want to plot the point P, -2, 5, 6. We want to draw a rectangular box with that point in the origin as opposite vertices. And then we're going to find what we call projections of P on the X, XY, XYZ, XZ planes. Think of projections as a shadow. So I draw my XYZ coordinate plane. All right, so I'm going to count 2 in the negative direction on X. I'm going to make 5 tick marks in the direction of Y, 6 tick marks in the direction of Z. So to build my box, I'm going to look at my XY plane here. I'm going to build a parallelogram. So think about from here, go parallel to that X-axis 2 units, parallel to the Y. There's our bottom base. Now, we'll go up 6. So you want to, again, make a measurement, edge of a piece of paper, whatever, mark off that distance. If you look at it, you see it go from black to purple. Then we're going to take that purple segment and you're going to draw vertical segments from every corner. Those are my other edges. Once you have those drawn, connect those 4 points. There's the top of our box. There's point P. -2, 5, up 6. So the projection of point P on the XY plane is the bottom of the box. That's in my XY plane. So again, think of this point as casting a shadow down onto the XY plane. That means you end up right at that point. Well, that means your your Z coordinate becomes 0. So the projection of my point is located at -2, 5, 0. So a pattern that falls into place here is a projection of a point onto this XY plane. Notice the Z variable is missing. Then that coordinate of that point P becomes a 0. Using that same philosophy over here, projection of P onto YZ. X is missing, so this X coordinate of my point becomes a 0. The projection of point P on the XZ plane, the Y variable is missing. So now the 5, the Y coordinate of point P, becomes my 0. So that's kind of a nice little pattern on how to find those projections of points onto those 3 planes of our 3-dimensional system. What is the length of the diagonal of our box? We're going to go from the origin to point P. There's my line segment. So origin's at 0, 0, 0. Point P is at -2, 5, 6. Use your distance formula. And again, you can subtract this in any order. 0 minus a negative gives me a +2. 2 squared, 4. 0 minus 5 or 5 minus 0. Either way, it's going to be a 5. Whether it's positive or negative squaring, it's going to make it 25. 0 minus 6, same thing, or 6 minus 0. You're going to get a 36 when you square 6 or -6. Add that all together, we get 65. The distance is the square root of 65. All right, in class we did the board work. Find the shortest possible distance of P to the y-axis. Well, that diagonal is already doing that, but that's not the shortest distance. You want to go to this point right here on this corner. That point would be 0 for the x, 5 for the y, 0 for the z, and just do the distance formula again with this point in 0, 5, 0. All right, example 3. Find the equation of a sphere with the center at -3, 2, 4 and tangent to the YZ plane. So here's my equation. There's the center. That's your H, your K, your L. Notice the sign change from the point into the equation. To find your radius, we have to be tangent to the YZ plane. That's like saying put the center, put a projection of this point onto this plane. Well, the X is missing. So your shadow is going to cover a distance from -3 to the 0. So that's going to be a distance of 3. So my radius is 3. Square it, you get a 9, and there's our equation. Example 4, you want to find the center and the radius. This is in general form, so what we need to do is we need to bring the y and the z term over to the left, leave the constant on the right. Group those together, x terms, y terms, z terms. Now the next thing you have to understand is that you have to have a 1x squared, 1y squared, 1z squared. So everybody on the left has to be divided by 3, and everybody on the right has to be divided by 3. So I'm just technically dividing both sides of my equation by 3. That's going to give me x squared, y squared minus 2y, now plus a blank, because this is where I'm going to complete the square for the y terms, plus z squared, 12 divided by 3/4. So minus 4z plus a blank. I'm going to complete the square of the z terms. If I'm adding two things on the left, I need to add two things on the right. Don't worry about this being a fraction. We'll be able to work with it. To complete the square, you take the b. That's this negative 2 or minus 2. Divided by 2 is minus 1. You square that, you put the 1 over here. Never square this number, otherwise you'll do too much work. Half of negative 4 is negative 2 squared, 4. So 1 plus 4 is 5. 5, convert that into a fraction with a denominator of 3 is 15/3, which we can add to 10/3. We'll get 25/3. Now the shortcut here is if, okay, let's say we did square the negative 1 and made it a 1. Now you got to factor it. What two numbers multiply to be 1 and add up to be negative 2? You're back to negative 1 and negative 1. So this negative 1 being squared and this y term being squared, that's going to factor your perfect square trinomial into this binomial being squared. So who's ever squared, put it in the binomial squared. Z squared, negative 2. Z minus 2, binomial squared. So I have my center at 0, 1, 2. My radius will take the square root of 25 over 3, which is 5 over the square root of 3. Rationalize the denominator to 5's radical 3 over 3. Okay, example 5. Describe in words what we get in our three-dimensional space if you had z squared equals 9. So you have to solve for z plus 3, negative 3, or positive 3, negative 3, I should say. Draw your xyz coordinate plane. So to take care of the positive 3, go up to positive 3. No, x and y's, make a plane parallel to the xy axis, that xy plane. Go down 3 on the z-axis. Make another plane parallel to the xy axes. So to describe that, you can say I have two planes parallel to the xy plane. One is 3 units above the xy plane, and the other is 3 units below the xy plane. B, x is greater than or equal to negative 3. So again, we're just going to look at the equal part. We'll take care of the greater than in a second. We'll go to negative 3 on the x-axis. Again, no z, no y. We get a plane, if you will, parallel to the yz plane. Now, the greater than comes into play is now greater than or equal to, so these all become solid lines, and it's going to head up the positive x-axis. So what's happening here is this first plane right here, remember, it's going up and sideways in both directions. And then we extend it towards the positive x-axis. So it's really not this box that's just getting longer. It's technically what we call a half space. Oops, one too many clicks. So we're going to infinity in the direction of positive z and negative z, positive y, negative y, and in a infinity in the positive x direction. So that's like saying that's half of my three-dimensional space. All right, so a half space of all points on or in front of the plane x equals negative 3. Next, we have y squared plus z squared equals 16. Kind of reminds me of the equation of a circle. So we are going to have a circle centered at the origin, making a circle in the yz plane with a radius of 4. Square root of 16 is 4. But because there's no x here, now this circle is going to continue in both a positive and negative direction. You're going to have infinite number of circles going along the positive axis, going along the negative axis. So here's my picture. It's this huge cylindrical tube. All right, another way you could say the first two sentences is just say you have a circular cylinder with radius of 4 whose axis is the x-axis, which means your center of that first circle, when you put in those infinite circles, all those centers are going to fall on